Lyapunov stability theorem.
Guessing in Russian.
Yes. Of course. Okay. So the theorem says simply the following. Let the origin, which I will just call x vector equal to 0. So I wanted to make this point. If you find some equilibrium point that's not at the origin, you can also always make a coordinate transformation to translate that to the origin. So it's useful when doing global stability, as you will see, to always translate your point to the origin by some convenient coordinate transformation.
So you both of those, you have to bring any point you want to the origin and then do your equation?
No, I'll show you what I mean in the example. But just know, just consider this point to be the origin. So let the origin x equal to 0 be in some domain called that D, which is a subset of Rn. So some origin point is in this domain D, which is a subset of Rn, and let this be in equilibrium point of your dynamical system. Okay. Then let this scalar function z, which goes from D to R, be a continuous and differentiable function such that the following three properties are true. Number one, that z of 0 is equal to 0. That z of x is greater than 0 for all x in this domain excluded from the origin. So at every point except 0, the function is positive. And further, the time derivative dz by dt is less than 0 for all x d excluded. If the following is true, then we say that x is equal to 0 is asymptotically stable. So, in other words, and a function that satisfies 1 through 3 is what we call a Lyapunov function. So that is a more practical way of determining whether something is globally or asymptotically stable. Now, it could be, point 3 is usually where people get caught up, of showing that the derivative is strictly negative. So if you are not able to show this, and instead all you can show, the best you can do, is dz by dz is less than or equal to 0, so a slightly weaker condition, then we just say the point x equal to 0 is simply just stable, not asymptotic. So I just wanted to mention that extremely important theorem because the Lassalle's invariance principle can be sometimes difficult to apply. Okay. So let us now see how this stuff works. So my challenge was to find examples that were not just examples for the sake of being examples, but maybe go into different fields like economics, chemistry, biology, so forth. So that's my plan, is to start in different subject areas and show you really that it's all differential. I can't do too much physics, obviously, because I don't want to scare half the class, which I did on the first day with the simple ball falling from the sky. So I will start with some examples actually from economics and game theory. So I promised you that on the first slide. And there's a lot of economics students in here for some reason. So that's a good thing. Okay. So let's do some examples. So in particular, we'll look at game theory. And in particular, the subset of what is called evolutionary dynamics. So consider, so this is not an economics course, obviously, which is probably a good thing. So I will skip over some of the economics theory, also because I'm not an economist. I don't know if you've noticed this. Okay. So consider a population in which individuals, which are called in this context replicators, exist in several different types. Each type of individual uses a pre-programmed or predetermined strategy. And passes, most importantly, this behavior to its descendants. So hence it's called replicator dynamics. So that's just our framework we are dealing with.
Is there like some sort of game they have where there's like the two blocks and they start to fall?
Say that again?
There's like a little game they have. I remember reading a map book and it's like the two blocks and they start growing and it's like
That is related to this. But the difference in that case is that it's discrete time systems. We are dealing in the continuous time domain. But it's almost the same thing. Yes. Okay, so let's put some letters and numbers behind what I just wrote. So, individuals are programmed to use or choose what we call in game theory pure strategy from a finite set. And we denote this set, just call it S. And within this set, we have a set of strategies. So call them S1 all the way to S. So this is capital S. And those are small. Okay. Now here's where the differential equations come into play. Okay. Now, let n sub I be the number of individuals using strategy S sub I. So Ni is a population proportion. And then, obviously, the total population is simply given by capital N. It's just the sum over all small n. Okay? So I equals 1 to k, let's say n. Okay. And furthermore, the proportion of individuals using strategy as I, we will denote by xi as equal to ni over. And that's the matrix. So you can see xi is always going to be a percentage, like between 0 and 1. Okay. Now, the dynamical systems part comes into play as follows. We are interested in predicting how the proportion of these populations will evolve over time, given that strategy set. So given our strategy set is so forth, how will the individual proportions of these populations evolve over time? So if 1/3 of the population chooses to use strategy S1, and 1/3 uses S2, and 1/3 uses S3, at a certain time later, what will that population distribution look like? Yes? But it's conditioned on the payoffs, which I'm going to write down.
So the choice is, it's a set, so they have a choice.
They have a choice. They have a choice between this finite strategy set.
But then at what point of time does it, what does it mean past the descendants? Is it the last strategy of the person used?
That's what we have to figure out. So this is where the interesting part comes into play. That is the question, right? How do they pass it on to the descendants? How is that evolving in time? So let's see. So using, I'll just say economics theory, because I don't want to get into now actuarial stuff. It's very boring, of course. Anyway, you can show that dxi by dt is equal to the following equation. I'll explain these symbols in a second. So pi si of x minus pi bar x times x pi. What in the world is all this mean? This function here, pi si of x, is called the payoff function. Payoff for using strategy Si, and pi bar is the average payoff. And we define the average payoff as follows. It's just an average. So it's going to be sum I equals 1 to n xi pi si. And furthermore, we have a constraint to this equation, naming that the population at any given time has to end up to 1, right? Because it's a percent. So we have a constraint of xi is equal to 1. So x1 plus x2 all the way to xk. So if I left you with this, you could answer any question, right? Yes? No? No? Who said no? I'm sad about this. No. Okay. So imagine my surprise when I took this course, and this is all that I was given, and then we had an assignment to do. You go figure it all out. It's not fun. Okay. So I will obviously now do examples for this. So let's see how this works. In other words, when you can understand the proportion of the population changes depending on the payoff. And by payoff, I mean the benefit you get by using a certain strategy versus another one. So it's dependent. So how do you get these payoff functions? That is the whole thing. So let's do an example. Do I want to do a fun example or do I want to do a bad example? Let's do a fun example. Okay. So the standard example in game theory is what we call the prisoner's dilemma. Now let me show you one. So example. Sorry?
Is this the one where you're mashes equal?
Yes. Precisely. So prisoner's dilemma. And it works as follows. So you as your friend, now we're talking about the population but let me simplify it to just a case of two people. So you and your friend are criminals. Sorry, there's no other way to present this example. And the idea is that you both get caught for a crime. But the police actually doesn't have any hard evidence against you. So you make a deal with your friend before you go into the interrogation room that no matter what, we are not going to squeal on each other. We are going to just avoid everything. So then the police say, if you both stay silent, you just get 1 year in jail, that's it. But then the police throw a twist on you. They separate you into 2 rooms. And they say, if you rat out your friend, you can walk away scot-free and he'll eat up on the jail sentence. So the idea is, what do you do in that situation? And we can now have to use game theory to figure out what is the optimal strategy for each person to do. What will they do? And if the choice they make, is it the optimal choice? Is it the rational choice? Is it the irrational choice? So let's see what happens. So the way you formalize what I just said is you set up what is called a payoff matrix.
This is the fun question.
I think so, yes. And you have 2 strategies in your strategy set. So as we will denote by one strategy, I will call it C. And another strategy, I will call it D. And the reason is the following. C we call the cooperate strategy. And D means to defect. So will you defect or will you cooperate with the police? In other words, defect, I just mean betray your friend. I told you, you had to be patient with the theory stuff I was doing, because now we can have fun for 2 weeks or so. And cooperate means to just with the authority. So let's put some numbers to this. In the Nash's original 1950s paper, he used this terminology, so I'm just sticking to the terminology. I know it's not, I was confused by it when I first looked at it, but Nash is not intuitive for some reason.
Could you need that chart to some extent? I just love to write.
Sure, no problem.
I'm just screenshot it.
Sure, no problem, I can come up with it. Okay, so what you do is you literally set up a matrix, like a table of possible options. So on one end, you put CD, and another end you put CD, like this. So the idea is that you fill in these rows and columns based on numbers you assign to picking a strategy. So I'm going to arbitrarily just put numbers here that make sense. But there's more general ways to do it that we'll see later. So for this specific example, I would just put in numbers here. And the payoff matrix here is given in terms of years of jail, or years of prison. So, if both friends cooperate with each other, let's give friend 1 3 and 3. So the idea is that the number you put corresponds to the payoff for the first individual. That's how it's done in game. So this means that if both friends cooperate with each other and don't run, they both will get 3 years in prison. But 3 refers to the focal individual, the one individual you're talking about. That's how you read these. If one cooperates and one defects, we'll give 0. If one defects and the other cooperates, we'll give 5 years of jail, and 1 year of jail if they both defect. So based on this now, we should be able to write down a dynamical system that describes the evolution of these strategies. So let's see. So the first step, I'm giving everything in terms of x1, x2 here, xi. So let me use that terminology. So let x1 be the proportion of individuals that use strategy C. Similarly, let x2 be the proportion of individuals that use strategy B. So then, our replicator dynamics equations look like the following. Then, so I'm just rewriting what I wrote on the board, but I'm just applying it now. So instead of dx by dt, remember I said I'm using the prime equation. So x1 prime is equal to pi of s1x minus pi of x times x1. Now, S1 is my first strategy, which is just C in this case. So this is just pi of C of x minus the average payoff x1. Now, what is the average payoff function? Let's compute that first. So, pi bar of x is equal to, remember, just by applying the formula, so it's x1 times pi C of x plus x2 times pi of. So that's the average payoff. It's just by applying the equations from before. Okay. Now the question is, what are the individuals, what is pi of C of x, what is pi of D of x? We read that directly off from the table. Okay. So, pi of C of x. You literally just go across the rows here. So, x1 refers to the rows here. That's how you refer to the equations. You refer to the numbers in the rows. So this would be 3x1 plus 0x2 for the pi of C of x. So pi of C of x, which is the first strategy in row 1, you simply write as 3x1 plus 0 times x2, just by reading off the row. So this is just 3x. Similarly, pi of D of x, you just go in the second row. So it's 5x1 plus 1x2. Is that okay? So I will always give you the tables, right? And ideally, as you will see, our answer depends heavily on the numbers I put here, as you can imagine. But the more general way to do this is to put any letter here, and then see how the numbers really affect your strategy. But just for an example's sake, an initial example, I'm making it a little easier. But it's okay up to here how I got pi of C of x and pi of D of x. It's just reading the rows directly off the table. Because x1 refers to strategy C, x2 refers to strategy B. So we know now all the different variables we have. We have pi C of x, we have pi D of x, and we have the average payoff. So now I can write down the dynamic. Okay. So, therefore, if you just work out the algebra a little bit more for the average payoff function, you get its x1. Actually, do I want to do that now? Let me make sure. Yeah, I'll work it. Okay. Yes, so I will just work out the algebra a little bit more. For this, so pi of x is equal to x1 times pi C of x, but pi C of x is just equal to 3x1. So this is just going to be x1 times 3x1 plus x2 times 5x1 plus x2. So that's what the average payoff is. And now I can fill in the blanks for the x1 dot and x2 prime. So therefore, but I cannot emphasize enough, the whole thing depends on just reading off the values of the payoff. So therefore, x1 prime is equal to 3x1 minus x1 times 3x1 minus 5x1 x2 plus x2 squared times x1. Just filling in the blanks. And similarly, x2 prime is equal to 5x1 plus x2 minus 3x1 squared minus 5x1 x2 minus x2 squared times x2. So we have a dynamical system now. You see that? A nonlinear system of equations for x1 and x2 that will describe completely how these states evolve. But what am I missing here? What am I forgetting to write? Very good. Subject to so, how many equations then do I really have here? Think about it. I can use the constraint to eliminate one of the equations. So how many differential equations do I really have here? One. That's why the constraint is extremely important in replicator dynamics, because it reduces the dimension of your system by one. So let's apply the constraint. You don't have to use it, but it's easier if you do. It's always easier to work with less equations. Well, that's the hope, isn't it? So far all I've done is just fill in algebra. I have not done anything, hopefully not complicated. Okay. Anyway, so if x1 plus x2 is equal to 1, I can eliminate one of the variables. It's up to you whether you want to work in x1 or x2. I'll choose x2. So this implies that x2 is equal to 1 minus x1. So then therefore, we can eliminate one of these equations. So x1 prime then, which I will choose to work with, and I will work it out for you actually. So minus 3x1 squared, minus 5x1 times x2, but now x2 is 1 minus x1. 1 minus x1, minus 1 minus x1 squared times x2. And you can, now you see we have one equation, and in terms of completely x1. And if you continue on this madness of simplification, what you will get is 3x1 minus 3x1 squared minus 5x1 plus 5x1 squared minus 1 minus 2x1 minus x1 squared times x1. And all of these terms cancel, like majority. So this actually ends up being something very nice. x1 squared minus 1. All that works and we get something simple there. So what happens now? So it's still a dynamical system in terms of we still have a differential equation. So we can still analyze it. Okay. So therefore, x1 prime equal to x1 times 1 minus x1 squared. I'm sorry, x1 squared minus 1. Completely describes the dynamics of this one equation. But as I said, I don't want to solve it, even though I possibly can in this situation, because it's just first order. It's not linear, but I want to use the tools that I've been talking about, even in this one-dimensional case. So how can I do it? So this is still in the form of x prime is equal to f of x, obviously. So the first step, remember I said, is to find the equilibrium. So let's do it. Equilibrium, which will occur for f of x In other words, when x1 times x1 squared minus 1. So what are the equilibrium points of this? Negative 1? But remember, okay, so you're right, but we're considering them to be physical populations. So it doesn't make sense to have minus 1%. So 0 and 1, right? So there are two equilibrium points that satisfy this equation. Namely, x1 is equal to 0 and x1 is equal to 1. So it's helpful to bring it back physically. What does this mean? It means there are two fixed points of this system. One where nobody in the population is choosing strategy C, and one where everybody is choosing strategy D. Right? Because x1 represents the population that chooses C, x2 represents the population that chooses D. So either everybody is choosing C or everybody is choosing D in the equilibrium point. There's no in between. That's the first thing we learn from doing this. So what else can we say? What else can we say? Now, yes.
Question, I'm sorry. Equilibrium.
They mean the points in your phase space that are not changing with respect to time.
I know, but what is it within this example?
In this example, it means that you have two possible states of this population. One where every individual is choosing to cooperate, or where everybody is choosing to defect.
Oh, okay.
So either 0 or 1. There's no half and half, if you notice. There's no 2/3 and 1/3. It's explicitly 0 and 1 in this case.
Right.
So the idea now, if you remember from my list last class, after you find the equilibrium points, what is the next step? He's looking at it. What did I say? Yeah, what is okay, so, and why do we want to compute the Jacobian? To determine which of these is stable, unstable, source and sink and so forth, right? Okay. In this case though, the Jacobian will just be the derivative of the right side because it's not a system, it's just one equation. So you can still compute a Jacobian of one equation, but it's just the ordinary derivative. So let's do that. So our 1D Jacobian, for lack of a better word, is just the derivative of the right side of this equation. Is the derivative of f of x. The Jacobian in general is a derivative matrix of f, as you know, but in 1D it's just the ordinary derivative of the function. So, if f of x is equal to x1 times x1 squared minus 1, what is f prime of x? Yes. 3x1 squared minus 1. And just like before now, we evaluate now the equilibrium points at this Jacobian and see what sign means. So, at our first equilibrium point, x1 is equal to 0, we see that f prime of 0 is equal to 3 times 0 minus 1, which is negative. Less than 2. Furthermore, we see that f prime of 1 is equal to 3, 1 squared minus 1, which is 2, which is greater than 2. So, we don't have eigenvalues, but we have signs of the function in the 1D case. So, the sign of the Jacobian corresponding to x1 is equal to 0 is negative. That means that this is a sink. And this is a source. In other words, what this means So x1 is equal to 0 is a sink of the system where x1 is equal to 1 is a sink. Because the derivative matrix is negative one case, it's positive. Just like having negative eigenvalues versus positive eigenvalues. And what that means is that, so, if x1 is equal to 0 is a sink, and x1 represents the population of people that use strategy C. So what does this mean then for the prediction? Which solution?
C.
Careful. How many people are using C? So then who is everybody using? X1 equals to 0 as a sink. Now, if x1 is equal to 1 was a sink, then everybody would be using C. But it's the way we chose our variable. So does everybody understand that? Yes?
So this means all the population that was using C is going to be 0 and that was going to be.
Exactly. So what this means is that every single individual, irrespective of his choices, will always choose to betray his friend. Will always betray. So x1 is equal to 0 means everyone will choose not C, but will always defect, will always betray your friend. I asked, actually, when I was writing this up yesterday, this example, I asked my family, so I have a younger brother, younger sister, and my parents. And both of my brother and sister both chose the defect option, as you would expect, because nobody wants to spend any time in jail. My mother actually chose the opposite one, which is very interesting. She gave me a lecture on how important loyalty is. It's not good, I don't know.
I just want to wrap my head around.
Yes.
Okay, so x1 equal to 0 is the same.
Yes, as we proved it.
Track that.
Yes.
So because the way we describe it as nobody is doing that,
Yes.
and that's the same thing.
Yes.
Everybody's there.
Yes, because if you look at it, remember, so even if you get confused about what this means, you still have your constraint, meaning that x1 plus x2 is equal to 1. That always must be true. So if x1 is equal to 0 is a final state of the system, it's a sink. Then x2 is equal to 1 is also a sink of the system. In another way of looking at it.
Can you define the global thing in this?
You can. And in fact, as I will show you in the next example, which is an upgrade of this example, because this is always less than to 0, irrespective of what x1 is, it's a global solution. Yes.
You're taking the same between the stable solution.
Yes. So in other words, when I talk about stability, sinks are always stable, sources are always unstable. Because everything approaches them, so we call them stable. And sources are repelled by everything, so we call them unstable. And saddles, by definition, are unstable because you don't have a clear attraction or repellability. Is this clear? More or less? Okay. So I want a full now geometric topology analysis of this solution by Monday. Now I'm good. But I see, I told you, because now you see, I didn't have to stop the example when we reached the equation. I knew exactly what to do, because we have no framework of how to analyze. Okay. Any questions about this? So I don't think I have time to finish the next example. I will introduce it.
So in terms of Jacobian, the single variable,
Yes.
it's just a decreasing or a decreasing.
Precisely. So that's the 1D analog of what a Jacobian is. Okay. So maybe just some more ideas about this, maybe just to elaborate on it. And I can post actually Nash's PhD dissertation on Moodle if you want to see it. Because a lot of this stuff came from these types of ideas. I think it was 20-something pages. Yeah. But I mean, it's the foundation of the field. Okay. So in fact, x1 is equal to 0. We say, and I'll prove this to you next class, but corresponds to what is called a Nash equilibrium. And in words, that means that individuals have to be able to evaluate the consequences of their actions. Of their actions. But compared to the results obtained by others who behave differently. And possibly switch or swap maybe to a better, but not necessarily the best. For the current strategy. So, in other words, you say that a population is stable. In other words, the population is stable when given what everyone else is doing, oh, my arm is hurt. I can't write like this. I have to put up slides maybe. What everyone else is doing, no individual would get a better result by adapting to a different strategy. Yes, precisely. And this is what Nash himself called the population view of his equilibrium, or I think it's called mass action interval. So that is really the motivation behind this. And the idea that you can prove this using these replicated dynamics equations. And next class I'll show you how to explicitly find Nash equilibriums in another example. So just to give you a preview, on Friday I will do the example of a rock, paper, scissors game, where there's a strategy between populations of choosing rock, paper, and scissors and see what happens in that population. And what are the equilibriums and so forth. So you can imagine that you've probably played this game a million times. After a very long time, everybody just keeps choosing the same thing, with 1/3 rock, 1/3 paper, 1/3 scissors. So you'll have something like that. But any questions at all? So for an exam question, I will never expect you to memorize any of the equations. I will always give you the equation. I expect you to do the analysis.
Because the goal was to get 0 jail time, that's
Yes.
why we said, like, for finding the equilibrium, what we said is to do 0 solve. So, like, if, for example, the goal was to get 3 of something, would you, like, solve for it?
So we didn't. to set the equation equal to 0 or to find the equilibrium.
Yeah.
But that has nothing to do with the jail time. That's in general how we find equilibrium. Always by saying the right answer. So what's the...
So like, I guess, measuring what level you choose, like, isn't that kind of dependent on what they want the end result to be?
In particular, but now see, the idea is that you have control over what the payoff will be. In that payoff matrix, I designed the question, but I put on the matrix. But in general, criminals don't have control over how many years in jail you get, right? So those are options that are given to you. You choose based on what is. But it's kind of a shady way of looking at it. There's a more general